Okay, hello again. In this one, we're going to combine our first order conditions for the household, finish the household problem, and also do some sanity checks. So to finish the household problem, we want to combine these first order conditions into some economically relevant quantities. And we do that by forming two equations. One is the Euler equation, and one is the supply curve for labor. And remember that we get the supply curve for labor from these two first order conditions. These are the derivative. This is the first order condition with respect to CT, and this is the first order condition with respect to LT. And we can just set these two equations equal to each other because we have the lambda t on both sides. So we'll get 1 over CT is equal to theta LT sigma L divided by WT. And remember that we can rearrange this so that we get the marginal rates of substitution for consumption leisure choice on one side, and we get the relative prices on the other side. So let's put all of the economic quantities on the left and all of the prices on the right. So I'm just going to bring this to here, and I'm going to bring this to here. And I'm going to put the theta on the left too. We'll think of the theta as like an adjustment to the wage that the households demand. So we'll have CT LT sigma L, and that's going to be equal to WT over theta. Now remember that this is, so this is the supply curve. This is the labor supply curve. And remember that this is the consumption leisure marginal rate of substitution. And you can see that if you just compute the derivative of the intratemporal utility function with respect to CT, and that equals 1 over CT. It's exactly this. And the derivative of the intratemporal with respect to LT is equal to exactly this top part, okay, this part here. And then if you divide them by each other, if you get this one divided by this one, which is exactly what a marginal rate of substitution is, it's the derivative of something, the ratio of the derivatives, you get this. Okay, that was all very sloppy and poorly explained, but you should see that if you were to take the derivatives of the utility function and divide them by each other, you would get exactly this. And on the right, we have WT. And implicitly, there's a PT down here, right? Because I did Walras's law right up front. I took out prices from the very beginning, but if we didn't take out prices from the very beginning, you would have a PT here, I believe. Okay, so there's implicitly a PT here. So on the left, we have the consumption leisure MRS. On the right, we have the consumption leisure relative price. This is consumption leisure relative price. That is the wage divided by the price of the consumption good. And then this theta shows up as a scaling factor. The higher is theta, the lower the effective wage, the perceived wage that we receive is. So we really hate to work. Even though you pay me 5, I only perceive that 5 to be worth 2.5, something like this. So you can understand theta as like a scaling factor on WT that, yes, even though you pay me, I perceive it to be much less because I hate working so much. Okay, so this is nice and good, but now we need to tackle these bigger messes. And normally, so an important fact that we need to know is that the standard solution in the standard problem, when you do not reduce IT, so normally, if you do not substitute IT, in the optimization, you will find that QT equals lambda t. Okay? So this is our base answer that we want to make sure that we can get back to. So what I want to check right now, because right now we can't really write down a nice Euler equation. Typically this qt would be lambda t, because qt equals lambda t, and this qt would be lambda t plus 1. And you can see that if that's true, we can get back to the Euler equation, right? I can factor out. So if that's true, how do I want to do this? I'm going to erase this so that we can see our equations here. So my system of scrolling up and down has collapsed. Okay, so let's right now assume that we're back in the base case. So just assume, playfully assume, this isn't true in our model here. But to make sure we didn't make a mistake, let's just assume that qt equals lambda t. And then let's try to recover the Euler equation from this. So we would end up with lambda t is equal to beta expectation at time t of lambda t plus 1 rt plus 1 plus 1 minus delta lambda t plus 1. And so there's a lambda and a lambda, so I can factor it to the left. So we'll get the expectation of lambda t over lambda t plus 1 equals beta expectation rt plus 1 plus 1 minus delta. And once we plug in our expression for lambda t, we already made this point. Once we plug in our expression for lambda t, then we'll see that we get the typical Euler equation back. So we get, remember that lambda t is equal to 1 over ct, which implies that lambda t plus 1 is equal to 1 over ct plus 1. So we can write this as ct plus 1 divided by ct, and this is an expectation, of course, is equal to beta expectation of 1 minus delta plus rt plus 1. Okay, and this is exactly our typical Euler equation. So this is kind of a sanity check to see that we didn't make any mistakes, really. At least in this equation, we didn't make any mistakes because we were able to get back to the normal. By assuming the normal condition, that qt is equal to lambda t, we were able to drop back to the normal equation. So remembering these baseline cases, at least having some inkling of what they should be, it's a way to check your work and make sure you didn't make any mistakes. Okay, but this is all not true, and we can't actually write any of this down, but we just wanted to do a sanity check. Now, what's the other sanity check we can do is we can try to recover exactly that relationship that we just talked about. So we just talked about how in the normal case, lambda t is equal to qt when we have no penalty, when phi t is the identity function, right? Like phi t is just equal to 1 for all choices of it. And we can get back to phi t is the identity function if we look carefully at phi t. We had that phi t was equal to 1 minus gamma over 2 it over it minus 1 minus 1 squared. It should be easy to see that phi t is the identity function, or scratch, phi t is 1 for any choice of it when. So this is true equals 1 if gamma equals 0. So what I assert is, so our test will be set gamma equals 0, recover lambda t equals qt. Again, here's the logic. We know that in the base case, this is true. And in the base, we could consider the base case to be a special case of the penalty function, where phi t is always equal to 1, right? So our law of motion of capital, we're thinking about it something like this. It's going to be kt plus 1 times it, right? So we do this, and this is like phi t if phi t equals 1 for all choices of it. So how do I get this 1 here? how do I make this sentence true? I make this sentence true by setting gamma equals 0. And you can see that if I set gamma equals 0, no matter what I pick for it, and no matter what is the value of it minus 1, I just get 1 out the other side. So now my strategy is set gamma equal to 0 and see if I can get back the base case, which is lambda t equals qt. And can we? Well, let's see. So I'm just going to make this really sloppy. I'm just going to do some erasing. So gamma is 0. That means all of this is 0. Hey, how come that didn't work? Something's wrong with my program. I apologize. One moment, please. Let's see. Window. Uh-oh. Uh-oh. Where is layers? Layer editor. Go to layer 1. Okay, I apologize for that. So gamma is 0, so all this is 0. Okay. And gamma is 0, so all this is 0. This whole thing goes away. And gamma is 0, so all this goes away. So as you can see, we're just left with a 1. And indeed, we recover lambda t equals qt. So we can be somewhat confident that we didn't make any mistakes because we were able to recover lambda t equals qt. Okay. Likewise, if we undo all that erasing, we should expect that in the steady state, lambda ss equals qss. Why? Because in the steady state, it equals it minus 1 forever, right? Yeah, there's no change to it in the steady state because that's the definition of the steady state. So we should be able to play the same game. We should be able to set it over it minus 1 is equal 1, and then we should get just lambda ss equals qss. And so we do it again. This is 1 minus 1 is 0, so this goes away. We have 1 minus 1 is 0, so this goes away. And we have 1 minus 1 is 0, so all this goes away. So we have exactly the same game. We're left with just this 1. Here, we change this to the steady state. And we get that lambda ss equals qss. So that's two different ways to check that we didn't make a mistake here. One was by setting the penalty function to equal 1 everywhere, by setting gamma equals 0. And one was by taking the steady state and checking that when it equals it minus 1, as in the steady state, that lambda t equals qt. Okay, so that's all there is to it. The firm problem is exactly the same in this one. The other steady state equations are exactly the same. Of course, you will recover the Euler equation as normal, right? Because we saw that when you're in the steady state, that lambda ss equals qss. So if you set, once you have that, you can come back to this equation, and you can just plug in lambda ss everywhere and solve as normal. And you'll get that rss equals whatever, 1 over beta plus 1 minus delta, something like this. And the firm doesn't change at all. So that's all there is to the capital adjustment case. All you need to do is make sure that you're very, very organized when you attack the Lagrangian for the household. So I think it's a very nice practice problem for practicing how to solve that household Lagrangian, which is the hardest part of the RBC model. So in the next set of videos, I'll look at the new Keynesian model where the firm will actually change. So hope to see you there.